how the different analogies between heat transfer and fluid mechanics can be used for calculating the heat transfer coefficient. That is what we have seen in the last class. Okay. So I will just quickly summarize that and then we will start with today's class. Okay. Just give me a minute. So is the slides visible to everyone?
Yes, sir.
So this is what we have seen in the last class. We started with the towards the end we started with looking at the analogies. We said that by doing the analogy between momentum transfer and heat transfer, then finally we will be able to calculate the transfer coefficient. Okay, so this analogy, there are different analogies given. The first analogy is Reynolds analogy. So what is being used in the Reynolds analogy is the dimensionless velocity gradient is equated to the dimensionless temperature gradient at the wall. So based on the equations which we have formulated here, we have obtained the dimensionless velocity gradient and dimensionless temperature gradient at the wall, and these are equated. In addition to that, the nu plus eddy momentum diffusivity and alpha plus eddy thermal diffusivity, these are equated. By equating this, what we get is Stanton number equals to F by 2, where F is nothing but the friction factor. So friction factor we can obtain directly using the correlations in terms of the Reynolds numbers, and based on that we can find out the heat transfer coefficient. So this becomes a one-step procedure, unlike the previous case where different correlations were formulated. Okay, that was the advantage with this. But then we said that the Reynolds analogy has some problem, because what Reynolds analogy is doing, it is assuming that the parabolic velocity profile across the cross section of the pipe, even though the flow is turbulent, isn't it? That's why we are putting this new this epsilon m and epsilon h here, isn't it? Okay, so but in reality, if you look at the turbulent flow in between, in the core, you will see that the rod like flow is there. So this particular thing is assumed by Prandtl. Prandtl assumed that the diffusive transport is there in the laminar sublayer, whereas in between the eddy transport is there in a turbulent core. So that is similar to a rod like flow. So with this assumption, Prandtl came up with another equation. He obtained the equation as Stanton number is given as F by 2 divided by 1 plus 5 under root F by 2 in the bracket Prandtl number minus 1. Okay, there are several other analogies also given by different researchers. Chilton and Colburn analogy is there, then some other are also there, but these are the mostly used analogies for calculating the heat transfer coefficient. So in all these analogies, F by 2 can also be represented in the form of JH factor. Okay, so F by 2 or F can be represented in terms of the Reynolds number. Also, F by 2 can be represented as JH factor. So that's why this entire equation is divided by 2. So that is given as 0.023 Reynolds number is to the power minus 0.2. Okay, so up to this we have seen in the last class. Is there any questions so far?
No, sir.
So let us start with the next topic today. So let us start with the natural convection. So remember when we started the convection, discussion on the convection, we said that it is easy to formulate the problem, but then solving is difficult. That's why this concept of heat transfer coefficient came into the picture. Also, we said that, whenever the convection is occurring, driving force may not remain constant, and therefore this concept of LMTD came into the picture, isn't it? Again, very often the heat transfer coefficient itself cannot remain constant. So therefore this concept of average heat transfer coefficient or the overall heat transfer coefficient came into the picture, isn't it? So these are the things which we have seen in the last class. Okay, now the similar ideas we are going to extend for the natural convection. Okay, so free convection or a natural convection primarily occurs whenever there is a motion in the fluid caused by the density difference. Okay, so a typical example is this experiment you might have conducted in your chemistry lab. Typically whenever we heat a liquid in a beaker, let's say, so what happens? The fluid particles, those are at the bottom, get the higher energy, and because of that their temperature increases, and because of that the density of the particles, those are at the bottom, decreases. However, the density of the particles, those are present at the top, will be still higher, isn't it? So what will happen? This lower density particle will try to move up, isn't it? And this high density particle will come down. So that circulation starts, isn't it? So this is a typical, natural convection things which we regularly see in the experiment, isn't it? Have you all seen this? Maybe this is the simple example. See, if you, many of you have, made tea, isn't it? So if you put a water in a, on a gas or something, you will see that the movement you start looking at, isn't it? You will see the movement in the particles, isn't it? There's some current starts coming in. Have you seen this ever? Hello?
Yes, sir.
So this is typical example of the free convection, isn't it? So the fluid particles which are at the bottom becomes lighter and they try to move up because of the buoyancy force, and that creates the motion in the fluid. Okay, so here the motion in the fluid is created by the density difference, and that's why we are calling this type of convection as a free convection, because no mechanical force is involved in this case. Okay. So the same thing is written here. The phenomena is called as a free convection or natural convection because no mechanical device or externally imposed force is used to create it. Okay, there are several, practical examples. I have given you one or two, but there are several examples which are of commercial importance. Commercial importance in the sense
Excuse me, sir.
Please go ahead.
Sir, the example which you gave of boiling water, in which is this not an example of forced convection because we are applying heat from outside?
No. We are okay. Good. You have pointed out this. Okay. Here the motion in the fluid we are not causing by using the mechanical elements. Look at the words. We have not used any mechanical device to create the turbulence in the liquid. The turbulence in the liquid is caused by basically a density difference because of the temperature difference at 2 points. Got the point?
Yes, sir. Yes.
Okay. So that is the difference. When we are saying that if you put some stirrer or something inside, then it is not a natural convection. Then the motion of the fluid is created by the mechanical part, isn't it? Got the point?
Yes, sir.
Okay, all right. All right. So natural convection is extremely important in a process applications. Why? Because if you visit any of the industries, you will see that if you visit any typical chemical industry, you will see that several steam pipes or several flow streams pipes are basically insulated. Okay, they are insulated primarily because you don't want it to lose the heat to the ambient. Okay, even though these pipes are insulated, what happens is the skin temperature of these insulation will still be higher than the ambient temperature. So some amount of heat will still be lost by natural convection. So whatever the air is around those steam pipes or something, there is a natural convection occurring between these insulated steam pipe and the ambient. Okay. So this thing is used whenever you are looking at the flow of a hot stream, or maybe sometimes a flow of a cold streams. Both the cases, the natural convection can lead to the heat transfer from ambient to the fluid. Okay, is it clear?
Yes,
Hello.
sir.
All right, so these are the numerous, some examples given here are the heat losses from the steam pipes, reactor, furnaces, etc. Okay. Okay. So in the last, topic, uh, forced convection, we have looked at the boundary layer, concept of the boundary layer. Again, in this case, also we are going to look at the concept of the boundary layer, but you will see the concept of boundary layer is slightly different compared to what we have seen in forced convection. Okay, so in this case, let us consider that we are having a vertical flat plate. This is the vertical flat plate is there. Again, for a time being, let's assume that the temperature of this vertical flat plate TW is higher than the uh, uh, bulk temperature of this fluid. Let's say T infinity. So T infinity is the free stream temperature, and TW is a temperature of the wall. Temperature of the wall is, let's say, higher than T infinity. And initially the let's assume that initially the fluid is at stagnant position. So fluid is not moving, unlike the forced convection where the fluid is moving because of mechanical force, isn't it? In this case, the fluid is not moving. Fluid is this free stream fluid. You can see here the velocity is 0. Okay, velocity is 0. But what you will see that since this temperature TW is higher than this T infinity, what will happen is the fluid elements which are very close to this wall will become lighter, isn't it? So their density is going to be lower than the density of the fluid particles which are there in this free stream. Okay. So what will happen because of that? Because of this density difference, what will happen is the fluid elements which are close to this wall will tend to move upward because of buoyancy force. Isn't it? Do you all agree? Do you all agree or not?
Yes, sir.
Yes, sir.
But the problem is when this fluid particles are moving up, because of no slip condition, the fluid particles which are exactly at this boundary here, they will have a no slip condition. That means they will not move, isn't it? So velocity of the fluid elements exactly at the boundary here is going to be 0 by no flow, this no slip condition, isn't it? So typical velocity profile which you are going to see in this case is something like this, where the velocity at this wall is also 0, velocity at this free stream is also 0, but in between you will have some velocity profile. Do you all agree with me?
Yes, sir.
Isn't it? So the fluid particle, even though the fluid particle at this wall are exactly at the wall are at a higher temperature and with a low density, but they cannot move up because of the no slip condition. However, the fluid particles which are slightly away from this wall can move up, isn't it? So we will have a typical velocity profile as shown here. Unlike the velocity profile which we have seen. So what type of velocity profile we have seen in forced convection? In a forced convection, if you remember, the velocity profile we have seen is something like this. I will draw for you again. A typical velocity profile seen is this. Do you remember this? Isn't it? This was the velocity profile which we have seen earlier in a
Yes.
forced convection. But in that case, the free stream velocity was v. In this case, the free stream velocity is 0. Okay. Again, so okay. So in the starting of this, card. Starting of this leading edge, initially the movement of the fluid will be in a laminar region, isn't it? But as we move up, as the distance from this leading edge increases, the velocity of the fluid element also increases, and from laminar boundary layer we move to a turbulent boundary layer, isn't it? So clearly, when we can have a turbulent boundary layer, it depends on 2-3 things. It depends on the viscosity of the fluid. It depends on the temperature difference between the fluid and the wall, isn't it? So again,
Sir, excuse me, sir.
please go ahead.
Sir, in case of forced convection, we could say that it is the leading edge because the fluid was entering to through this side only. But here it is not moving. It is uniformly distributed before the temperature was raised. It was uniformly distributed. So how can we say that it is the leading edge, and on moving forward we are going in the turbulent region?
So yes, you are absolutely correct, but we will still get a boundary layer like this. Why we are saying that? See, this is the top. Okay. Maybe I just draw a container here. Then you will, okay. Different color. So let's say this is the container I am having. Okay. This is the container I am having. I have put a hot plate suddenly here at time t equals to 0. Okay. So what will happen? The fluid particles which are here, these are already at the top, na? Isn't it? So initially what you will see that the fluid particles from here will move, and with that movement, these are also going to drag some of the particles which are there here. So that's why this boundary layer thickness get increases, because here see, amount of heat added as you move from this end to this end, that increases. And the movement is taking place in the upward direction because the buoyancy force is going to work in what? It is going to work in the upward direction, isn't it? So this type of boundary layer you are going to get because the movement of the buoyancy force is only in the upward direction. That is the only reason. Otherwise, we shouldn't have got this type of boundary layer. Did I answer your question?
Yes, sir. Yes, sir. Got it.
So this typical boundary layer similar to what we have seen in the forced convection we are getting, because the direction of the force is in the upward direction. The buoyancy force is only going to have in the upward direction. That is why we are getting this. All right. So still we are calling this as a leading edge because of that. But you are absolutely correct in saying that we should not call this as a leading edge. Okay. All right. Okay. So analysis, how, okay, so remember what we have said in the forced convection. We said that, you know, things are going to become complicated. Let's appreciate the same thing again here, isn't it? So in order to analyze this entire system, what we have to do, we first have to solve the momentum balance. Then we have to solve the energy balance, and then finally both momentum and energy balance together coupled way we have to solve to get the heat transfer occurring in such cases. Do you all agree? Yes or no? So typically what we will do, typically we will take a differential element in the system, then apply a force balance. when we will apply the force balance, typically in this case, the x direction, we will take it in the upward direction, in the direction of the buoyancy force, isn't it? Or movement of the fluid particle. So if you apply a Navier-Stokes equation, if you apply the momentum balance, what we are going to get is a Navier-Stokes equation in a x direction, which is given here. So this is the Navier-Stokes equation which we are expected to get in this case, isn't it? So again, we are assuming no. So the fluid movement is uniform along the z direction. So z direction is what? Perpendicular to your plane of your computer, isn't it? So there is no velocity distribution along the z direction. It is uniform. It is uniform. So that's why we have written this Navier-Stokes equation only in a x direction, but there is a component in a y direction is also how the velocity is going to change on a y direction, that is also will be there, isn't it? But no z direction. So this is the Navier-Stokes equation which we have obtained. This you probably have derived from the first principle earlier in your transport phenomena. Also similar thing we have done when we have looked at the force balance earlier. Okay, but these additional things we have not considered. Okay. So I am starting with the Navier-Stokes equation in a x direction. This is the typical equation which we are going to get it. So this term is a pressure force. This is nothing but the force because of buoyancy, and this is the viscous force. Okay. Now in this case, this pressure force will also be, see, in this case, no mechanical movement is taking place. So whatever the pressure force is acting on the fluid is primarily because of what? It is primarily because of how much is the height of the liquid present, isn't it? Do you all agree with me? Yes or no? If I look at this particular container, whatever the force acting at any point here, that depends on what is the height of this container, isn't it? Yes or no?
Yes, sir.
So that pressure force is primarily because of that. So we can represent this pressure force in terms of the density and the acceleration by gravity, isn't it? So here rho infinity into g, that will be the pressure force acting here, isn't it? Because no external pressure is generated because of mechanical element. It is all because of whatever is there, whatever the fluid elements are there. Okay, so this dou p by dou x we can eliminate by using this. So what we are going to get is g into rho infinity minus rho, where rho infinity is nothing but the density of the fluid particles at the free stream, whereas rho is nothing but the density of the fluid particles at temperature, at higher temperature than the free stream temperature T infinity, isn't it? So this is at temperature T. Do you all agree with me? Hello? So remember, this buoyancy force will act only when this density is lower, isn't it? Correct. So g into rho infinity minus rho, this particular term further we can replace using the coefficient of volume expansion. So coefficient of volume expansion is defined here in this case as minus 1 by rho, dou rho by dou t at constant pressure. And if you represent this in terms of the densities, we can write this as minus 1 by rho, rho infinity minus rho divided by T infinity minus T. So if you rearrange this, rho infinity minus rho can be given as beta into rho T infinity minus T. And this minus sign will also be counted here. So if you put that in this original equation, this G rho infinity minus rho, this term we can represent in terms of temperature difference. So now T is the temperature of the fluid, whereas the T infinity is the temperature of the fluid at free stream. So this is the temperature when the some heat is because of some heating, the temperature of the fluid element is going to increase. So that new temperature is T, whereas T infinity is the free stream temperature. So this is going to be a temperature difference. So this represents the momentum balance. Similarly, we can apply the energy balance. Energy balance is going to give us this another equation. Okay. And also there will be a continuity equation, isn't it? So all three equations has to be solved simultaneously in order to obtain the uh, the complete picture of natural convection. Okay, so these three equations has to be solved simultaneously. So clearly the problem is complicated if you wanted to solve it using the first principle. Do you all agree? Yes or no? So we have to solve all three equations simultaneously to get the correct picture, isn't it? So formulation is not difficult. Difficulty is in solving. Okay. So typically, instead of doing all these analysis from first principle, the same thing which we have done in the forced convection, we are going to do here also. So we are going to formulate the correlations of heat transfer coefficient, and those correlation of heat transfer coefficient can be directly used to find out the heat transfer occurring in the given system. Of course, the heat transfer obtained using those correlations will not be very accurate, but it's okay. You will not have a complicated mathematics coming in between. Okay, do you all agree?
Yes, sir.
So another thing to appreciate before we move to the next slide here is, even though we are not going to look at this entire analysis, but one important thing which we have understood in this slide, and what that important thing is, unlike the forced convection, in a natural convection, the term which is going to become more important is nothing but this G into beta. This term is going to be very important, isn't it? So this beta coefficient of volume expansion and this G, which is nothing but the acceleration by gravity, these two terms are going to become more important here, because the entire movement of the fluid particle is taking place because of this, isn't it? Coefficient of volume expansion and the acceleration of gravity, isn't it? So the weight of the particle is acting in a downward direction. The density difference or a buoyancy force is acting in the upward direction, isn't it? So both these factors are important, isn't it? So these are the additional thing which are coming into the picture compared to what we have seen earlier in the forced convection, isn't it? So now, remember, in the forced convection also we started with the discussion on what type of equations we are going to get if you do a first principle balance. But then we have moved to a dimensional analysis where we said that these are the important variables. These are the important variables in the system, isn't it? And using these variables, then we have came up with different dimensionless groups that will be important in a forced convection. So in this case also, this analysis we are not going to do it, but at least this analysis gives me the glimpse that what are the different variables important in my system, isn't it? So one of the important variable which we have not included earlier is G and beta. Do you all agree?
Yes, sir.
Okay, all right. So again, as I said, we will rely on developing the correlations for heat transfer coefficient. So typically you will see that the correlations in the forced convection are in terms of a Grashof number. What is Grashof number? That we will see in the next slide. So when we are having two parallel plates, and let's say the plate which is at the lower surface, the lower surface of the lower plate is at a higher temperature. In such cases, the heat transfer can take place by a pure conduction when a Grashof number is less than 1700. Okay, so this is the limiting case we are getting. Remember, in the earlier case also, when we have looked at forced convection, we said that the flow is going to be laminar when the Reynolds number is less than 5 into 10 raised to the power 5, isn't it? So similar way here, we are going to have a Grashof number. Okay, so unlike the Reynolds number, in this case, the dimensionless number which has to be looked at is a Grashof number. So now what is Grashof number? Grashof number is nothing but buoyancy force by viscous force. So unlike the Reynolds number which we have used earlier, remember in the forced convection we have used the Reynolds number. isn't it? What is Reynolds number? Inertia force by viscous force. Unlike that, the Grashof number is buoyancy force by a viscous force. Okay, so this Grashof number is going to decide whether the flow is going to be laminar, turbulent, what type of heat transfer coefficient we are going to get, what will be the value of that will be decided by a Grashof number. Okay, so higher the difference between temperature of the wall and the fluid, higher is the induced flow. When the fluid velocity is large enough, the free convection boundary layer changes from laminar to turbulent. Okay, so as the Grashof number is a higher value, then it will change from laminar to turbulent. Again, a Grashof number. So remember, whenever we are looking at the heat transfer, either Reynolds number is there or a Grashof number is there, but there is another number which is common, which is nothing but a Prandtl number. Prandtl number remains common throughout the heat transfer. Okay, whether it's a natural convection, whether it's a forced convection, whether it's a another any type of system, Prandtl number you will see that it is common. Okay, so very often instead of writing the correlation in terms of a Grashof number, people write the correlations in terms of the Rayleigh number, and Rayleigh number is nothing but what? Grashof number into Prandtl number. So this is similar to the Peclet number. Remember, Peclet number is what? Reynolds number into Prandtl number. Similar to that, but Peclet number becomes effective in a forced convection. In a similar manner, the Rayleigh number is nothing but a Grashof number into a Prandtl number, and it becomes important in a natural convection. So this is defined as, this is the equation. So G into beta delta T L cube divided by nu. Nu is nothing but the kinematic viscosity multiplied by a thermal diffusivity alpha. So that gives you a Rayleigh number. So for a laminar to turbulent transition on a flat plate, Rayleigh number should be greater than 10 raised to power 9. So if my Rayleigh number is greater than 10 raised to power 9, then our flow is going to be turbulent. Okay, again, in this equation, you can see this beta is the additional variable which we have defined as a coefficient of volume expansion. It is nothing but a coefficient of volume expansion. So this coefficient of volume expansion is defined using this equation. But for an ideal gas, very often we are looking at the system in which the air we are looking at, and with some amount of error, we assume that the air is also an ideal gas. In such cases, the beta is obtained as 1 by absolute temperature. For an ideal gas, this beta is given as 1 by absolute temperature. So 1 by T is going to give you a coefficient of volume expansion directly. But of course, this is true only for an ideal gas. Okay, is it clear to everyone?
Yes, sir.
All right. So again, let's make a dimensional analysis. Again, I will not go in a detail because this part we have seen with lot of details earlier, but I am trying to give you a glimpse of what we have done here. So remember, in this case, unlike the forced convection, we said that the heat transfer coefficient depends on thermal conductivity, Cp, rho, mu, velocity, and diameter, isn't it? That's what we have, diameter and temperature. That's what we have said in the forced convection. Similar to that, in a natural convection, we are saying that the heat transfer coefficient depends on thermal conductivity, specific heat, density, viscosity, and this new variable Bg, which we have not looked at. Again, instead of diameter, here we are taking a L because we are taking the heat transfer from the flat plate. So the distance from the leading edge is what we are taking as L. So this L we have taken here, and delta T, temperature difference between free stream and the wall, the hot or a cold wall, isn't it? So these are the different variables which are going to have an effect on heat transfer coefficient. Correct. So once we know this information, then we can do the dimensional analysis. Remember, that is what the first step is. First, to obtain what are the different variables which are important in a system, isn't it? So we have obtained these variables from our a priori knowledge on the heat transfer system, and also looking at this analysis, we have understood that this G and beta is also a important parameter to look at, and therefore In this case, remember, in earlier case, the velocity used to be important, but here the velocity is not important because this velocity is induced by what? Velocity is induced by G and beta. So that's why instead of velocity in a forced convection, we are taking this G into beta in a natural convection. Do you all agree? Does it make sense what I'm saying?
Yes, sir.
Okay. So again, you can do a same dimensional analysis. So here, how many variables are there? 1, 2, 3, 4, 5, 6, 7 variables are there, isn't it? 7 variables are there. And how many fundamental quantities are there? 4 fundamental quantities are there, isn't it? So 4 fundamental quantities are there, 7 variables are there. So that means 3 dimensionless groups you are expected to have. That's why you are getting 3 dimensionless groups. HL by K is a Nusselt number, CP mu by K is a Prandtl number, and this entire bracket L cube rho square beta G delta T by mu square. This is nothing but a Grashof number. Okay. So again, also you can, assume a power law type of relationship here, and then equate their coefficients. So if you do that, you will be equating the coefficient for mass, length, time and temperature. And if you solve these, you will get this equation. It's just easy. So you just write the dimensions of each of these variables here, and then equate these with the coefficient corresponding to H, and then find out the remember, in this case there are 4 equations are there, but how many variables you will have? 1, 2, 3, 4, 5, 6, 7. That means 3 variables will be represented in terms of the other 4, isn't it? So you will get basically the 3 dimensionless groups like this. Okay, is it clear? I'm not going in the detail, but this anyway is solved here. If you look at the K, what is the dimension of K? Dimension of K is MLT minus T raised to the power minus 3 into capital T raised to the power minus 1. So what is the H? H is this. So if you compare M, you will get just 1 on the right hand side, but for this K, this M raised to the power A will be there. So that's why A is added. Similarly, in CP there is no M, so there is no B here. Then for rho there is another M is there, and mu there is M, so that's why you will get A plus C plus D equals to 1. Similarly, you can equate for L. Similarly, you can equate for T and capital T, and then you can represent these 3 variables, maybe E, F and G in terms of ABCD. If you do that, finally you will get this equation. Is it clear? Does it make sense? Hello?
Yes, sir.
So this we have already done a similar analysis for a forced convection earlier. So that's why I'm not doing this in a more detail. Is it okay? Can you do it yourself?
Yes, sir, we can.
Okay.
Yes, sir.
So from this analysis, what information we have obtained? We have obtained the information that whenever we are looking at the natural convection, the 3 dimensionless groups which I need to look at is a Nusselt number, which is this first factor, Nusselt number. Then the second factor, which is nothing but a Prandtl number, and this last factor is nothing but a Grashof number. So these are the 3 numbers which are going to be correlated. So that means all the heat transfer correlations need to have these 3 dimensionless numbers, isn't it? Do you all agree? This is what we have said, isn't it? So these 3 dimensionless groups will be used in the correlation. Of course, how these are correlated, the dimensional analysis is silent on that, isn't it? The dimensional analysis is silent on that. So sometimes you can, represent a very good power law type of relation like this, but very often you will see that people have made a complicated correlations also, which do not have that flavor of power law. But that's okay, because in terms of the dimensional analysis, that is allowed. isn't it? These are related with each other. How these are related? That part is not clear, isn't it? Do you agree? Do you all agree? Does it make sense what I'm saying? Or lost somewhere?
Yes, yes.
If something is not clear, please say so. Is it clear to everyone?
Yes, sir.
Okay. So let's look at some of these correlations. Of course, I will show only few correlations. These are anyway there in the book, but just to appreciate the concept, I am giving you these correlations here. So the first correlation is by Churchill and Chu. This is for free convection from a flat surface. So here you can see this Nusselt number is related to a Prandtl number and Rayleigh number. So Rayleigh number is just nothing but a multiplication of Grashof number and Prandtl number. So it doesn't matter. You can see that only Grashof number, Prandtl number and Grashof number, Prandtl number and Nusselt number are used in this correlation. Can you see? Isn't it? So this equation is for the entire range of Rayleigh number. But for a laminar range, there is another equation is given by a Churchill and Chu. So this is the another equation which is given by Churchill and Chu, which is only for a laminar region. Again, for a free convection from the cylinder, one can use a power law type of relation also, where we can have a Nusselt number related to the Rayleigh number calculated in terms of diameter raised to the power n, where C and n are the parameters which you can obtain depending on what is the range of the Rayleigh number which you have obtained, isn't it? So depending on the range of the Rayleigh number, one can select C and n and use it in this equation and calculate the heat transfer coefficient. Clear? So remember, this equation is exactly following the power law relationship the way we have written here, isn't it? But this equation, these two equations, you can see there is no power law type of relations used, isn't it? These are slightly more complicated than power law equations, isn't it? Again, free convection from the horizontal cylinder is again given by Churchill and Chu. These are also related with Nusselt number and Rayleigh number. Again, Nusselt number and Rayleigh number both are calculated in terms of diameter. So one more thing to look at, this is only for the horizontal cylinder. But if you are having a vertical cylinder, in case of a vertical cylinder, the same equation which we have derived, which we have obtained for the vertical flat plate has to be used. In that case, the breadth will be equal to the circumference of the cylinder, and that you can check by checking this particular criteria. So if you are having D by L is greater than 35 divided by Grashof number raised to the power 1/4, in that case what you have to use is you have to use the same correlation of the flat plate for even a cylinder, vertical cylinder. Okay, is it clear to everyone? Last equation is again given by Churchill. So Nusselt number again given as 2 plus some complicated term are there. But here you can see that Nusselt number here in this case also related to the Rayleigh number. But Rayleigh number is calculated in terms of diameter. Okay. So again, this factor of 2 is used because you can see that the convection for a convection in a Stokes flow, the Nusselt number is obtained as 2, isn't it? So that 2 is, they have further retained this 2 in a free convection also, free convection from the sphere. Unlike the cylindrical surfaces or a flat surfaces, very often we have a confined confined rectangular cavities we have. In a confined rectangular cavity, and in fact this is of extreme, you will see that the situation of confined rectangular cavities are of lot of practical importance. Okay. So in a vertical rectangular cavity, the correlation is given by McGregor and Emery. So in this case, the Nusselt number is calculated in terms of the width of this enclosure, and that is given as HW by K. It is given as 0.42 Rayleigh number, again calculated in terms of width of the rectangular cavity raised to the power 0.25 into Prandtl number raised to the power 0.012 multiplied by L by W raised to the power minus 0.3. Here L is the length of the cavity, whereas W is the width of the cavity. Again, this equation is valid for a range of Rayleigh number between 10 raised to the power 4 and 10 raised to the power 7. Also, the Prandtl number has to be greater than 1. Greater than 1 and less than 2 into 10 raised to the power 4, and L by W should be between 10 and 14. Is it clear what type of situation we are looking at here? Hello? Hello? Are we lost? Hello?
Yes, sir. You are.
So I'm really sorry that so many correlations are there. So you don't have to remember this, isn't it? Everything is open book. So this is also I wanted to discuss with you a little bit. So maybe once we do these things towards the end, we have to discuss several things. Okay. So all these correlations are already there in the book. You don't have to remember, except Ditters-Boelter equation that you have to remember, because that is very often people ask. So that you can remember. Other than that, none of the correlation you have to remember. Okay. Uh, all right, but I am showing you all these correlations because then and then only you will appreciate that for a different geometries, how different correlations are used. What are the different factors important there, isn't it? That's why I have given only a few correlations here. But if you look at the book, there are multiple correlations are there, more than what I am representing here. Okay. So another equation is given. This is a slightly simpler equation. Nusselt number again calculated in terms of width of the rectangular cavity is given as HW by K. So here again W is a width of the cavity, which is, and the Nusselt number is given as 0.046 Rayleigh number raised to the power 1 by 3. And this equation is valid when Rayleigh number is between 10 raised to power 6 to 10 raised to power 9. Prandtl number is between 1 to 20 and N by W is between 1 and 40. So these are the different correlations which are used for calculating the heat transfer coefficient when we are looking at the natural convection. Okay. But our life may become, complicated. Our life may become sometimes complicated. Why I am saying this? So see, in this case, in a natural convection case, we said that the the motion in the fluid is caused by density difference, isn't it? That's what we have said. The motion in the fluid is caused by density difference. But let's say if you are having the forced convection or the some mechanical element is also there. So both forced convection and natural convection are present. Then what correlation one has to use? For instance, if you are having some, pipe flow is there from bottom to up. So there is a uh, uh, mechanical movement is also there, but at the same time, because of temperature difference, also the particles can move, isn't it? For instance, if I am having, let's say, a system like this, let's say if I am having a pipe flow like this, isn't it? So this is the mechanical pump maybe we are having. Let's say mechanical pump is pumping the fluid here. Is coming. Also the temperature here, let's say temperature here is, let's say 20 degrees Celsius, and temperature, sorry, The temperature here is, let's say, 200 maybe, and the temperature here is, let's say, 100. What will happen? So not only there is a movement of the particle because of the mechanical element here in the upward direction, but also this density difference because of this temperature difference will also be active here. Do you all agree or not? Does it make sense what I'm saying? Hello?
Yes, sir.
So both the factors are going to be there, but which correlation you should use? Isn't it? Now the situation is complex because now both mechanical movement is also there and there is a movement because of the density difference, isn't it? So which correlation you should use? So whenever we have a combined free and forced convection, first we have to find out which regime is more dominating. Whether the forced convection regime is dominating or whether a free convection regime is dominating or both are present, that we have to first find out. How we can find out? Remember, the forced convection is represented by using what? Forced convection is governed by what? Forced convection is governed by Reynolds number, if you remember, isn't it? Free convection is governed by what? Grashof number. So that's why we are taking a ratio of Grashof number divided by Reynolds number raised to the power 2. If we are taking this ratio, if this ratio is very, very low, this ratio is very, very low, what it means? So, okay, so if this ratio is very, very high, if this Grashof number raised to the power Reynolds number square, what does it mean?
So that free convection is dominating over forced convection.
Free, so okay, so if we are having the Reynolds number, okay, so if this Grashof number, okay, so this Grashof number is, let's say, very high compared to the Reynolds number. Grashof number is very high to the Reynolds number. That means what? That means what? The free convection is dominating over the free convection is dominating over the forced convection, isn't it? So I think I have written it wrongly. I just corrected. Just a minute. So I think this should be a free convection, isn't it? Do you all agree?
So your screen
No.
is not visible.
Sorry. So is it correct when this Grashof number by Reynolds number is very, very small compared to 1, very, very small compared to 1, then the forced convection regime is dominating. Do you agree?
Sir,
Yes,
yes,
sir.
it's not visible.
It's not visible.
Yes, sir, it's not visible.
Let me just add, sorry. Is it visible now?
Yes, sir.
So you can see that this Grashof number by Reynolds number, this is very, very small compared to 1. Then the forced convection regime is dominating. Do you agree?
Yes, sir.
Yes.
Similarly, when the Grashof number by Reynolds number square is much higher, that means the Grashof number is much higher compared to the Reynolds number. So clearly the free convection regime will be dominating. Correct?
Yes, sir.
Yes.
But when Grashof number and this ratio is equivalent to 1, in that case both mixed convection is there. That means both forced convection as well as free convection are there. So what we have to do is, first we have to find out these ratios, and depending on that, if the forced convection regime is dominating, then you will be using the correlation corresponding to forced convection regime. If the free convection regime is dominating, then you will be using the correlation for free convection regime. The complications comes when both forced convection and free convection both are there. Okay, so in that case, when forced convection and free convection both are present, then we have to use the Nusselt number will be calculated as based on the correlation of the forced convection and the free convection. The Nusselt number is calculated using both, but it will be raised to the power m, where m is in general is equals to 3. Is it clear? So you will be calculating a Nusselt number from the forced convection correlation, and you will basically this cube of that value you have to take. Again, you have to add or subtract from the cube of the free convection values. Okay, but when you have to add and when you have to subtract, that depends on the direction of the buoyancy force. For instance, the same figure which we have drawn earlier. In this case, let's say this is 100 degrees Celsius and this is 200 degrees Celsius. So clearly you can see that the buoyancy force will also be acting in this direction. Do you all agree? And the direction of the flow is also same, isn't it? Direction of the flow is this. Yes or no? Hello?
Yes, sir.
So both direction of the flow and direction of the buoyancy force both are same, and in this case this plus sign has to be used. But when, let's say if I make this 200 but I make this as a 400, then what will happen? Or maybe I'll just keep it this as a 100 and this as a 200, but direction of the flow, let's say I reverse. Then direction of the force I have reversed. So what is happening now? The buoyancy force is acting in a upward direction, but the flow direction is in a opposite direction, isn't it? So in that case, this minus sign will be there. Do you all agree? Does it make sense?
Yes.
Okay, so this is what we have to use. So whenever both the mixed regime is there, in that case, both forced convection correlation as well as free convection correlation has to be used, and these values has to be, raised to the power m. So m is in this case usually the value is 3. Is it visible?
Sir, does this mean that the Nusselt number for forced convection will always be greater than free, because we are using minus only for free convection?
Yes, absolutely, because forced convection, remember that mechanical element is pushing, isn't it? So more fluid particles will be moving. Nusselt number will be definitely higher in a forced convection.
Okay.
So that is the reason typically you can see that the heat transfer coefficient, you will get a higher heat transfer coefficient in forced convection compared to the natural convection. Very often this is most of you will see that always it is the case. So forced convection, because of mechanical element are driving the turbulence, you will have a higher heat transfer coefficient compared to the free convection. All right. Let's look at one example. So a refrigerator is placed near the partition wall of a room such that there is only a 4 cm gap is present. So the system is like this. There is a, maybe I will draw it one more time for you. So this is the wall. This is the wall, let's say. This is the refrigerator wall. Okay, and there is a partition wall. So this gap is there. This gap. This gap is given as 4 centimeter. 4 centimeter. Okay. The surface of the refrigerator facing the wall. The surface of the refrigerator, this surface of the refrigerator is facing the wall. Okay. So this height is given. This height is also given. This height is given as 1.6 meter. 1.6 meter is the height is given. And the breadth which is in the perpendicular direction to the plane, that is given as 0.8 meter. Okay, if the temperature of the surface, this temperature of this surface is 22, whereas the temperature of this wall, this refrigerator wall is 30. Calculate the rate of heat gain by the cooler surface, isn't it? So this is the typical example which we see in our home also, isn't it? We generally put our refrigerator very close to the wall, isn't it? So there is a very small gap present between the refrigerator wall, which is their backside, and the wall. Very limited space is available for heat transfer, isn't it? Can you see the point? Hello?
Yes, sir.
So in this case, let's calculate everything. So the in a forced convection, we find out the properties of the fluid at the average temperature of the wall and the fluid stream. That's what we do. But in a free convection also, we are taking this average temperature. So this is the 22 degrees Celsius temperature is here. 30 degrees Celsius is this wall temperature. So the average of that becomes 26. We are assuming that the air is present in between this cavity here. So property of the air we have obtained from the table which is there at the back side of the book. So these are the properties which we have obtained at this 26 degrees Celsius. Again, the L is given, width is given. So L by W we have calculated, that comes out to be 40. We have calculated again the Rayleigh number in terms of this cavity. Remember RAW. So RAW will be what? Grashof number calculated in terms of W into Prandtl number. So this is GB delta T W cube divided by kinematic viscosity into thermal diffusivity. So if you calculate the Rayleigh number comes out to be this. Okay, so this Rayleigh number, then we have used the same correlation which is there. This correlation we have used, this particular correlation we have used in this case. Here you can see the Prandtl number is exactly at L by W is almost 40, so we can use this. Rayleigh number is also between these two limits. And air we are using, so air the Prandtl number is around 1, so we can use this. There is no problem. So this 0.7 is there, but this is very close to 1. So without worrying, we can use this equation. There's no problem. Okay. So this particular correlation we have used, we have obtained the Nusselt number in terms of the width. And from this Nusselt number, we have calculated the H, heat transfer coefficient. So H comes out to be 1.313. Once we have obtained the heat transfer coefficient, then we can find out the rate of heat transfer as using the Newton's law of cooling as HA delta T, isn't it? This directly we can obtain. Is it clear to everyone? Hello? Hello?
Yes, sir.
Does it make sense to everyone? Okay, so this is the end of this natural convection chapter. So before we move, I have few things to ask. So I think we have 7 or 8 lectures available. How many lectures are available with us? Can anybody tell me?
So 13.
13 lecture we will get, or 7?
So up till now 13 lecture recordings are there.
No, recording of 13 lectures are there, but how many we are left, I'm saying.
The left.
So up to the 1st March is the 1st April is the last teaching day, isn't it? So my guess is we will get, and one more buffer day is there after that. So we will get, typically I guess we will get 6 or 7 lectures, correct? 6 or 7 lectures we are going to get. What I feel is the topics which we are left with are the topic we are left with is, after this we will have the condensation. Boiling and condensation is there, so that will take 1 day or maximum 1.5 day. Radiation I will take 2 days, 2 or 3 days I will require for radiation, and heat transfer, heat exchangers will take 2 days. So 4, 5 lectures or 6 lectures I will require. Other than that, we need to carry out 2 quizzes, isn't it? 2 quizzes we have to carry out before the final examination. So what I am planning is, so by what date you all are going to onboard? Any? So as per the guidelines given by Dean Academics, I think your end term will be in a physical mode, isn't it? If I'm.
Yes, sir. Yes, sir.
Yes,
So
sir.
by what date you all will be onboarding? Any date? Can you tell me?
Sir, I guess by the end of the first week in March, mostly people will onboard, and officially it is 14 March. Like after 14 March, the evaluation will be offline.
Okay, so maybe so then we do not have, because even though 14 March is given, but not everybody will come before 14 March. So maybe quiz 1 and quiz 2 both we have to conduct online mode. That's what I'm just trying to figure out. Am I correct? I thought if we can do a last quiz offline, because in online, in general, I feel is, if you miss a small thing here and there, and you lose the marks, isn't it? So in a offline mode, you can write the entire answer. I can, go through your steps and you can get some step marks, isn't it? That's what I have seen. So at least I wanted to have one quiz to be done offline, but it seems like we do not have that choice. Am I correct?
So if we have a quiz after 14th of March, then I think we can take
But
it.
after 14th of March, when your end term is going to start?
End of March from April.
Acha. So okay. So can we maybe then after the last class we will have the third quiz we will have offline. Third quiz we will have offline in a classroom directly. But second quiz we will have a offline. But can we have a quiz 2 maybe next week? Is it possible? Next week on 3rd. Can we have a next quiz on 3rd? That will be online quiz.
Yes.
So we will have a quiz in a class time. We will not have any class on Thursday, but we will have a quiz from same 9:30 to 10:30, something like that. Does it make sense?
Yes, sir. Yes, sir.
So that is one announcement. Another announcement is so next week one more tutorial we will have. So can we prepone that tutorial maybe on Sunday, this Sunday? Anytime, whatever you say, tutorial I'm saying. Tutorial number 6, can we do it on this Sunday? So you will not have a tutorial, and on the next Wednesday, we will not have a tutorial. Can we have it on Sunday? Anyway, we record it, isn't it?
Yes, sir. No problem. We can have it on Sunday.
Sunday 9:30
Yes.
to 10:30.
Hmm.
So 9:30 to 10:30 we will complete the tutorial, and on 3rd we will have a quiz, online quiz, the similar way we have conducted our minor examination. Again, the entire modality and everything will be same as what we have done for this particular quiz. Is it okay?
Yes, sir.
So what will be the syllabus for that quiz?
Syllabus will be whatever we have done. Some So whatever we will complete by Monday, that will be the syllabus. So I think we have covered now conduction, unsteady state conduction, heat transfer coefficient we have covered, forced convection we have covered, and today we have covered this natural convection. And Monday probably we will start with radiation. So the initial part of the radiation also we will cover by that time.
Monday there is no class.
Sir, actually on Monday there will be a holiday.
Monday there is no class?
Yes, sir, it is given that on 26, 27, 28 and 1 of March we have a holiday.
Yes,
No,
sir,
no,
it's
we will have a Monday class. We will not take a holiday. Why? Because they are, otherwise there is no advantage in that. They will schedule it on some Saturday.
No, sir, it is mid-sem break, I guess.
It is mid-sem break, sir, winter break.
Yes, sir.
Mid-sem
According to
break is
that,
from what?
calendar.
Let me check. Mid-sem break you are saying. Mid-term, mid-semester break is from 26 to 1. 26 to 1. So no class on Monday, that's what you are saying? And are they planning to have some class on some Saturday later? Let me just check. See, this March 12 Saturday will work as per Monday timetable. Got the point? Hello? Hello?
Yes, sir.
So they will schedule it on some Monday, some Saturday later on. So it is better to get it done on Monday itself. But of course, if you have any reservation, we will not have a class. So what do you say? Can we have a class on Monday?
Yes, sir, don't have it because I'll be onboarding that day.
Acha.
No, sir.
No means what? Not to have a class or to have a class?
Sir, not to have a class because some of us are onboarding plans in the mid someday.
So okay. No, all right. Whatever you say, we will follow that. So no class on Monday, but we will have a syllabus whatever we have covered till date in quiz 2, and that quiz 2 will be on 3rd. Okay. All right.
So means up to free convection.
Up to free convection, everything will be there. Another thing which I wanted to say is I am going to activate this mid-sem this feedback. Mid-sem feedback I am going to start. Please feel free to write and suggest the changes if something is not good. Okay. I generally read through all your comments. Okay, I read through all your comments, everything, and I take your comments seriously. So if you feel something has to be changed, something is not correct, feel free to write. Another thing which I wanted to say is I have corrected your minor things. Some anomalies were there, so that I have corrected. Please check your marks. I think in between, after one regret, some people got deducted their marks, but that I have corrected. Now whoever got the marks earlier, there is no reduction in that. Okay. All right.
Yes, sir.
Okay. And also those who have sent some queries, I have tried to resolve their queries also. Okay. Okay, then let us stop here and see you on Sunday. All right.
Okay, sir.
Okay, thank you everyone.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.